Assalamu alaikum. Let's start lecture 6 of CS218 Data Structures and Algorithms. In the last lecture, we learned about the big O notation. We learned how to find big O notation of functions. We learned the rules of the big O notation. And we learned how to find big O notation of code fragments. We continue with analysis of algorithms and use chapter 4 of book 1 and chapter 2 of book 2. Let's pick up from where we left. The question is the same. Find the big O notation for the given code fragment. Find neg is a function which takes a list called int list. N is the length of the int list. For I in range n, if int list I is less than 0, return I. After you come out of the for, you return none. What does this function do? This function takes the int list and then checks for a negative number. If it finds a negative number, it index I. It returns this index. But if it exhausts the whole list and does not find a negative number, it returns none. So actually this function is searching for a negative number in a list. What is the best case for this algorithm? What is the worst case for this algorithm? If you want, you can pause the video and think about it. I will discuss this in later slides, and it will be nice if you already know the answer. So now I am starting with best case analysis. Remember, the best case happens when the algorithm has to do the least amount of work. You can see that n equals len in list is O1 and it executes every time. The for loop iterates from 0 to n minus 1. Every time that you start executing this function, you have to enter the for loop. In the body of the for, we have an if condition. If the if condition is true, we move into the body of the if from where we exit the function. So what if the first location I check satisfies the if condition? This would mean that I would start the first iteration of the for, move into the if, the condition would be true, and I will exit out of the function. This would be the best case of the algorithm. So the best case is there is a negative number at int list 0. What lines execute in the best case? N equals len int list, this will execute. For I in range n, this will execute, but only for I equals 0. If int list I is less than 0, this will execute and the condition will be true. And then I would execute return I. And that would be the end of it. So n equals len int list is O1. The for loop iterates just 1. This is O1. Inside the for loop, a condition is checked, O1. Moving into the if, I return a value, O1 again. All of this is happening in a sequence. So O1 plus O1 plus O1 plus O1. The best case analysis is O1. Worst case analysis. Worst case is when the algorithm has to do the most work. This will happen if the for loop iterates n times. This can happen in two ways. A. There is a negative number at int list n minus 1. The loop iterates n times and returns n minus 1. B. There isn't any negative number in int list. The loop iterates n times and the function returns none. If we are suffering through case A, then we will spend O1 time on n equals len int list. Then we will spend On time on the for loop, and the total O notation of the fragment will be O1 plus On, which is On. But if we are progressing through case B, we will spend O1 time on the first line n equals len int list, On time on the for loop and its body, and O1 time on return none. O1 plus On plus O1 is On. So the worst case running time is On. Average case analysis. For average case analysis, we must know every possible situation that can happen, and we must also know the probability of occurrence of that situation. So, possible situations are like these. There is a negative number at 0th index. Let the probability for this be P naught. There is a negative number at int list 1. Let the probability for this be P1. Moving on, there can be a negative number at int list n minus 1, the last index of the list. Let the probability for this be Pn minus 1. Finally, there is a chance that there is no negative number in int list, and let the probability for this be Q. How do you calculate the average case? You find the number of locations that you will need to access for a particular situation and multiply this number with the probability of that situation. Tn is summation over I from 0 to n minus 1. Locations checked if negative number is at I multiplied with probability at I plus n into Q. Why n into Q? If there is no negative number in the int list, then we will have to check the full list, that is n locations, and the probability of this case is Q. So I have multiplied the number of locations checked multiplied with the probability in the last term. Writing this down, opening the summation, we have this equation. Tn is 1 into P naught. If the negative number is at 0th index, we need to check only one location to find it, plus 2 into P1. If it is at index 1, we will check two locations to find it. Continuing, n into Pn minus 1. If it is at the last index, we will have to check n locations to find it, plus n into Q. Assume that the list is very large and the probability of not finding a negative number at any index is very small. This means that Q is approximately equal to 0. Assume that the list is not sorted in any order. Then the probability of finding a negative number at any index is equal. If the list is sorted in ascending order, you will find negative numbers only in the beginning. If it is sorted in descending order, you will find negative numbers only at the end. But saying that it is not sorted at all means that the negative number can be anywhere. That is, P0 is equal to P1, which is equal to Pn minus 1, and all of these Pi's are equal to P. We know that the sum of probabilities of all outcomes of an experiment is 1. So P0 plus P1 and continuing to Pn minus 1 plus Q is equal to 1. But Q is equal to 0 and all Pi's are equal to P. So N into P is 1 or P is 1 upon N. Now we come to this equation where we have substituted all Pi's by P and Q with 0. We get Tn is 1 into P plus 2 into P plus continuing N into P. Take P common and we have 1 plus 2 all the way to N multiplied with 1 upon N, which is the value of P. Now we apply the formula for summation of arithmetic series and we come to this equation. Notice that N in the numerator will cancel N in the denominator. Tn will be N plus 1 whole divided by 2, which means that the average case of this algorithm is ON. Big omega notation. Given functions fn and gn, we say that fn is omega gn if there are positive constants c and n naught such that fn is greater than or equal to cgn for n greater than or equal to n naught. Look at the picture. When n is close to 0, fn is less than cgn. Then it rises up. Then it falls down again. But n naught is a point beyond which, moving towards positive infinity, the value of fn is always greater than the value of c times gn. N naught may not be the point at which the two curves cross. N naught is just a point beyond which, if you move towards positive infinity, every value of fn is greater than or equal to every corresponding value of cgn. The lowest value of n naught must be 1. It is an integer. C is also greater than 0, but it is a real number. What is the difference between big O and big omega? By now, you must have solved this. Big O gives us the upper bound of the function. Big omega gives us the lower bound of the function. Find Gn such that Fn is omega Gn. Fn is 8n plus 5. We need to prove Fn is greater than or equal to Cgn. We need a C and n naught and a function Gn that satisfy this relation. We know that 8n plus 5 is greater than or equal to 8n. This is true for all values of n, but we are interested in values of n greater than 0. So the smallest possible value of n naught, is 1. Take C to be 8. So Gn is n and Fn is omega n. The linear function is a lower bound on the growth of Fn, or the linear function grows slower than Fn. Fn is 3n log n minus 2n. Again, we need to find a gn which can serve as omega notation for our Fn. We know that 3n log n minus 2n can be written as n log n plus 2n log n minus 2n. I have split 3n log n into n log n and 2n log n. Now I am going to take 2n common from the last two terms. This is what I get. N log n plus 2n whole multiplied with log n minus 1 is greater than or equal to n log n. But this will only be satisfied when 2n log n minus 1 is greater than or equal to 0. This can happen when n is greater than equal to 0 and log n minus 1 is greater than equal to 0, which means log n is greater than equal to 1, which means that n is greater than equal to 2. Now, there is one condition n is greater than equal to 0 and the other n is greater than equal to 2. If I take the second condition, the first condition will also be satisfied. And this is what I do. 3n log n minus 2n is greater than or equal to n log n for all n greater than equal to 2. The smallest possible value of n naught, is 2. C is 1, Gn is n log n, Fn is omega n log n, or the linear arithmetic function is a lower bound on the growth of Fn. The linear arithmetic function grows slower than our function Fn. Fn is 5n square minus 3n plus 2. We need to find the omega notation. We know that 5n square minus 3n plus 2 is greater than or equal to 5n squared minus 3n. I have only made a smaller side for the function. I can remove 2 because 2 is positive. But I cannot remove 3n because there is a minus sign with 3n. So if I remove 3n, the function will actually become larger. I am looking for a smaller side. So if I remove 2, I will get a smaller side, 5n square minus 3n. What to do about this 3n? Again, I do the same thing. I split 5n squared into 2n squared plus 3n squared. And then in the last two terms, I will take common. I will take 3n common. This is what I do. Now 2n squared plus 3n whole multiplied with n minus 1 is greater than or equal to 2n squared. But this will happen when n is greater than equal to 0 and n minus 1 is greater than equal to 0. Which leads us to say n is greater than or equal to 1. A condition that would satisfy both is n is greater than equal to 1. So here we are. The smallest possible value of n is 1. Take C to be 2. Gn is n squared and Fn is omega n squared. The quadratic function is a lower bound on the growth of Fn. Fn is 8 log n minus 2. We need to prove Fn is greater than or equal to Cgn. We know that 8 log n minus 2 is greater than or equal to 6 log n plus 2 log n minus 2, splitting 8 into 6 and 2. 8 log n minus 2 is greater than or equal to 6 log n plus 2 whole multiplied with log n minus 1. This is greater than or equal to 6 log n. But this will happen when log n minus 1 is greater than or equal to 0, which means log n is greater than or equal to 1, which means n is greater than or equal to 2. The smallest possible value of n is 2, c is 6, gn is log n, fn is omega log n. The logarithmic function is a lower bound on the growth of fn. The big omega notation of a function is its fastest growing term disregarding the constants. If fn is 3 raised to n plus 2n square plus 3, then fn is omega 3n. You don't need to prove anything. You just look at the fastest growing term, that is omega notation. I know that you would say that I said the same thing about big O. I will come back to this point in a while. Fn is omega gn if and only if gn is O Fn. In easier words, if gn is the lower bound of Fn, then Fn is the upper bound of gn. The big omega notation provides the tightest asymptotic lower bound of Fn. Fn is 5n cubed plus 4n. All polynomial functions of degree less than 3 have smaller rate of growth than Fn. The linear arithmetic function, polylogarithmic function, log n, and constant functions have smaller rate of growth than Fn. So all functions with a smaller growth rate can be the big omega notation of Fn. It is mathematically correct to say Fn is omega n raised to d, d is less than 3. Here n raised to d is representing polynomials of degree less than 3. It is correct to say Fn is omega n log n. It is correct to say Fn is omega log of n raised to a. It is correct to say Fn is omega log n. And we can also say that Fn is omega 1. But we need the tightest lower bound, the smaller growth rate function that is closest to Fn. Which function would be the most suitable for big omega? We know that 5n cubed plus 4n is always greater than or equal to 5n cubed. From here we write Fn is omega n cubed, and this is the best answer of all that we have written. All statements in red are correct, but when somebody asks you for omega notation, that person is expecting you to give a function that is closest to his function but slower in rate. So the answer in purple is the best answer. Asymptotic conventions. 5n square plus 3n is greater than equal to 5n square, which means 5n square plus 3n is omega 5n square. But it is poor taste to mention 5. So 5n square plus 3n is omega n square. 5n square plus 3n is greater than equal to 5n, which means 5n square plus 3n is omega n. But it is poor taste to use a lower order function for big omega notation when a higher order function is available. So 5n square plus 3n is omega n square. 7n square is greater than equal to n square plus 6 log n. But it is poor taste to use two terms to describe big omega notation and say 7n square is omega n square plus 6 log n. Instead, we use a single term that would suffice and say 7n squared is omega n squared. Big theta notation. Given functions fn and gn, we say that fn is theta gn if there are positive constants c1, c2 and n0 such that c1gn is less than or equal to fn, which is less than or equal to c2gn for n greater than equal to n0. If you look at the picture, you can see that beyond n0, as we move towards positive infinity, the value of fn is always between the corresponding values of c1gn and c2gn. Gn is a function which is growing nearly equally to our function fn. Theta notation provides a function that is both the upper and the lower bound on the running time of an algorithm. More about big theta. For any two functions fn and gn, fn is theta gn if and only if fn is ogn and fn is omega gn. Theta notation exists for all polynomials. Theta notation only exists when the O notation is same as the omega notation. You would say this will happen for all functions. Yes, you are right. There are some algorithms for which the O notation is different and the omega notation is different. So for them, theta does not exist. Find Gn such that Fn is theta Gn. Fn is 3n log n plus 4n plus 5. We need to prove C1Gn is less than equal to Fn, which is less than equal to C2Gn. We know that 3n log n is less than equal to 3n log n plus 4n plus 5. How did I do that? I simply took out 4n and 5. So only the first term will obviously be less than or equal to the full function. Then 3n log n plus 4n plus 5 is less than or equal to 12n log n. How did I do that? I replaced 4n with 4n log n and 5 with 5n log n. This is true for all values of n greater than 1. Why? Because log n is not defined for 0. So the smallest possible value of n is 1. C1 is 3 and C2 is 12. So Gn is n log n. Fn is theta n log n. The linearithmic function grows with Fn. Little o and little omega. Given functions fn and gn, we say that fn is little o of gn if there are positive constants c and n naught such that fn is less than cgn for n greater than equal to n naught. If you remember the definition of big O, there is a less than equal to sign, but here there is only a less than sign. This is the difference between big O and little o. Little o notation gives us a function that is higher in growth rate than our function, but it is never equal to our function asymptotically. Given functions fn and gn, we say that fn is little omega of gn if there are positive constants c and n naught such that fn is greater than cgn for n greater than equal to n naught. The same difference exists between big omega and little omega. Little omega gives us a function that is slower in growth rate than our function, but the two functions are never asymptotically equal. Fn is little omega of Gn if and only if Gn is little o of Fn. So if Gn is smaller in growth rate than Fn, then Fn is higher in growth rate than Gn. Using calculus, let limit n tends to infinity Fn upon Gn be C. You must have calculated limits in calculus. If C is equal to 0, see both the functions are racing towards infinity. If C is equal to 0, this means that Gn is faster than Fn. So Gn hits infinity faster than Fn. And when it hits infinity, this becomes 1 upon infinity. And 1 upon infinity is 0, so C is 0. What made this happen? A higher growth rate of Gn. If C is 0, then Fn is little o of Gn. If C is infinity, look at the limit again. Fn and Gn are two functions racing towards infinity. If Fn hits infinity first, that is Fn has a higher growth rate, the whole limit will become infinity. If C is infinity, Fn is little omega of Gn or Gn is little o of Fn. If C is a member of R and C is not equal to 0, this means the limit is not 0, the limit is not infinity, the limit is some other number. How will this happen? Two functions are racing towards infinity and they are doing so at nearly equal speeds. Then Fn is theta Gn. If you see an indeterminate form during calculation of limit, you must apply L'Hopital's rule, and I know that you have read it in calculus. If the limit does not exist, this means that there is no relation between the two functions. Some people confuse best and worst cases with upper and lower bounds. Let us look at a story. In a daredevil game show, the contestant was asked to pick one of two boxes and eat the insects inside it to move to the next level. The boxes were marked A and B, but the contestant could not see the markings. Box A could hold 15 to 35 insects and box B could hold 10 to 50 insects, but the sizes of both boxes were same. Worst case for the contestant. He picks box A and it has 35 insects, or he picks B and it has 50 insects. Best case for the contestant. He picks A and it has 15 insects, or he picks B and it has 10 insects. So the lower bound of the best case is 10 and its upper bound is 15. Worst case has a lower bound of 35 and an upper bound of 50. So the best and worst cases are not the same thing as upper and lower bounds. And in some situations, we have best cases with lower and upper bounds and worst cases with different lower and upper bounds as depicted in this story. I hope that this helps you. Have a look at your homework. Provide values of C or C1 and C2 and N0 to prove These three. The second question is, using calculus, find the asymptotic relationships between these functions. You need to use the limit here. You do not need to submit this homework. This is just for your practice and understanding. So what did we learn today? We learned to analyze for best, worst, and average case complexities. We learned about the remaining 4 asymptotic notations, and we realized that we could use calculus as a tool to find out the asymptotic relationship between two functions. Things to do: read the book, note your questions and put them up in the relevant online session, and email your suggestions to me if you have any. Take care and Allah Hafiz.